Okay, we're going to start by looking at the very bottom of this. I wasn't really paying attention at the end of yesterday, and I didn't really think about how important it was. Okay. All of the triangles that we've done on this page. All the triangles that we've done on this page have had a perpendicular bisector that passes through the opposite vertex. You guys see that? Because they've all been on, all of the vertices of these triangles have been on the perpendicular bisector of the triangle. Okay, this does not always happen. These are special triangles. Okay, sometimes we'll have, a lot of times actually, we'll have triangles that are doing other things. Like this. Okay, so the perpendicular bisector for this side goes like that. I mean, it's a little crooked, but you get the idea. Okay, it's chopping the side into two, okay? It's not going through the opposite vertex. Does everybody see what we're talking about? These are special because by definition they have to be isosceles, okay? This is only true of isosceles triangle. Like all the scalene triangles we've seen, they're going to be more like this. Okay, so only special ones have this happen. Okay, so I just need you to know that the perpendicular bisector for a side of the triangle does not always pass through the opposite vertex. Like even if, let me get another isosceles triangle. Woo! Did not. Okay. Okay. All right. So you can see which two sides I've made the congruent sides, right? Okay. Now if I do the perpendicular bisector of one of the congruent sides, it's not going to go through the opposite vertex. Okay, so I essentially have the same picture. But if I go through the other side, and I'm bisecting this side instead, and I go 90 degrees, you see I'm missing my opposite vertex. Okay, so perpendicular bisector for the side of a triangle does not always pass through the opposite vertex. Everybody happy? Or at least if this made you miserable, you can at least understand why. Okay. It might not have made you happy, but hopefully you're not confused. All right. So now we're on to angle bisectors. We've done this with constructions, okay, but we haven't really had a whole lot of theorems about it. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Okay, so if I wanted to measure how far point C was from side PB, could I measure the distance like this? No. If you were thinking about it really hard, the answer is no. Whenever we do distance, we have to go perpendicular distance. Okay? Otherwise, I could make something that was really short just seem really long by going the long way. Okay? Does that make sense? We have to have a standardized way to talk about a distance between two things, or it doesn't even make sense. Like, what are we comparing it to? Okay, so you can see here that my angle bisector PC, the ray, has made two congruent angles, angle APC and angle BPC. So I can say that the length AC is equal to the length BC. Boop, boop. Kind of makes sense, right? That should kind of make sense. That's going to be true anywhere you go on that bisector. Okay, so they picked those points, but if I went here, it's also going to be true there. I just have to make sure that I'm going perpendicular. Okay, and then this is the same as that. Yeah. You're thinking, I like where your head's at. You said ray. Do you want to say something else besides ray? Because a ray is infinite. It doesn't have a length. So what segment? Yep. Okay, so what she's saying is, don't we also know this? And yes, we do. Okay, you can probably see that I have a reflection with line PC being my axis of symmetry. Everybody see it? Okay, cool. All right, so the converse of that theorem says that if a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of the angle. So if we have this congruent to that, then I know this angle is congruent to that angle. All right, here we go. All right, so they're telling me that M is equidistant to J and L. So what do I know about these cute little angles? They are congruent. So is this the angle bisector theorem or its converse? Good, this is the converse. Okay, so what do we do? Yeah, we set up an equation. I know that that measure has to be equal to that measure because those angles are congruent. Thank you, definition of congruence. So I can say that 3a plus 20 is 2a plus 26. I'm getting a is 6. Okay, I'm not done. I still have to find the measure of angle MKL. Oops, I missed. Okay, so I'm just going to take that 6, substitute it in. 2 times 6 is 12, plus 26. Thank you. Did you say 38? I wrote 48, sorry. One of us is very tired. Okay, are we good? So she checked it by substituting into the second one and making sure that she got the same thing, which is a really good way to check your work, especially if you know that those angles have to be congruent. Okay, let's do this guy. Given that the measure of angle WYZ is 63, XW is 5.7. And ZW is 5.7. This is what you were asking about, Danny. If these two are congruent, what do I know about? Okay, the angles are congruent, and what else? I have this one and this one, right? So then I also know this one and that one, and this and this. All of the things. All right, so I have to find the measure of XYZ, the angle XYZ. XYZ. Okay. What do you guys think? Yeah. So I don't know that it directly tells us that these two have the same measure. However, if they all have to add up to 180 in a triangle, right? So that we've already used 90, right? We've used 63, so how much is this little one? 27. So that one's also 27. So it only leaves 63. So it has to be the same. Everybody see why? Okay. So the measure of angle XYZ is 63. Okay. Did I mess up? I did? Okay, so we got to the bottom of that. This is not XYZ. This was XYW. And then we have to add those two together.
No. The question
I know that, but this one's 63. Okay, so now we're going to find this one by adding them together. Am I crazy? Okay, so what's 63 and 63? Okay. 126. All right. Whew. Whew. All right. Thank you. Okay, given that YW bisects angle XYZ and WZ is 3.05, find WX. Okay, so this is 90. We're using the same amount here in each triangle regardless of whatever it is. We could maybe say it's like 60 or something. So whatever it is, the same amount is left for this one and this one. Everybody see that? So I can use my, is it my converse? Okay, you can just tell by looking at it, what is it? Yeah. Okay. Given that line L is the perpendicular bisector of DE, so let's code that. We know it's perpendicular. We also know that it's bisecting DE, so these two lengths are the same measure. We know that DE is 20.8. We know that DG is 36.4. EG is also 36.4. What is EF? Yeah. Okay, like shooting fish in a barrel. Okay, remember that the distance between a point and a line is the length of the perpendicular segment from the point to the line. So if I want to know how far is this point from this line, I don't measure the distance crooked. That doesn't even make sense. Okay, I do perpendicular distance. Okay? Okay. All right, let's keep it moving.